Okay, now we're going to look at how to measure the strength of an acid. And so I'll start out with this first example here, where we talk about the auto-ionization of water. We talked before about the fact that water can be amphiprotic. And according to the Bronsted-Lowry acid-base definition, water can act as both acid and base. So here's a case where you have two water molecules in association with each other, and what happens is that one of them will give up a hydrogen to the other, forming the hydronium ion, leaving behind the hydroxide ion. So what we have is this situation where we can look at this as an equilibrium expression. So if you remember from chapter 15, an equilibrium expression shows the concentration in molarity. In the brackets, we say that that's big M, molarity, the concentration of the products divided by the concentration of the reactants. But if you remember, one of the special things about the K expressions is that you eliminate liquids and solids, pure liquids and solids. So we wouldn't put that in. So this is the K expression for the auto-ionization of water, and it becomes very important when you're talking about finding a pH. And so since it's water, there's going to be a value that's constant for this ionization of water. And that constant, just like we had K constants in chapter 15, we have a constant for the water dissociation. It's called water dissociation constant. And so the hydronium ion times the hydroxide ion is always equal to this value, 1 times 10 to the negative 14. Again, I feel like I, didn't tell you this more. I've mentioned it a few times, but maybe not enough. You may see oftentimes that hydrogen can be substituted in for the hydronium ion. The hydronium ion is just a hydrated hydrogen ion. So it really comes from the idea that water molecules, because of their high polarity, because of their hydrogen bonding, they're always associated with one another. And so they really form the hydroxide ion and the hydronium ion. But again, you may see it written in this way as well. So what we want to find out would be, what is the concentration of each of those ions if this is always 1 times 10 to the negative 14? And so all you would do is you would do a little bit of algebra, and you would come up with x squared is equal to 1 times 10 to the negative 14, and you would find that your x is equal to 1 times 10 to the negative 7. So in water, the hydrogen ion and the hydroxide ion are always equal at 1 times 10 to the negative 7. And that's when we would have a neutral solution. But if your hydrogen ion is greater than your hydroxide ion, you'd have an acidic solution. And if your hydroxide ion is greater than your hydrogen ion, you'd have a basic solution.